second lab in power supplies that deals with a step-down transformer. So what do we mean by step-down transformer? Yeah. You almost said power, didn't you? Don't say power, right?
It's a habit.
Yeah, but don't say that because we don't change power, right? Like I said, Alabama Power would love that if they could step up power with a transformer. That means their generators would be little old tiny things instead of being these big old things. They'd be little old tiny things because the transformers would step the power up, but the transformers don't step up power. All they do is change the voltage and the current. So most people say they step the voltage up and step the voltage down, which is fine, but the current goes in the opposite direction because that is the power source, right? You understand that? We're not talking about what's going on with the load. We're talking about the power source. So the higher the voltage of the power source, the less current's required to deliver that power. So this is why your high wattage devices are designed around high voltage, even at your house. So at your house, all your high wattage loads are designed around 240. And all your low wattage devices are designed around 115, right? Or they're 120. So this is the transformer. So we have a dual voltage transformer. We have a dual primary winding secondary, dual voltage primary, secondary. And our ultimate goal is to get the same voltage on our secondary, whether we put 240 or we put 440 over there, right? Everybody understand that? Are we okay? This is inside the lab. This is the one on transformers. This is PS2. So PS1 is when you go in and you're checking out the disconnect, right? Y'all understand? PS2 is actually where we're going to wire our transformer. And what do we have coming out of our disconnect? So we should know that already. Most y'all measure those, right? So what do we cut? What's the voltage out of our disconnect? What's that? So y'all made all those measurements, and then we went home and nobody remembers what you measured. Probably a little more than that. If it was optimal voltage, it would be 208. But usually measures a little bigger than that because it's what we call a Y connection. And we talked a little bit about Y, right? Y and delta. Y and delta, Y provides a common. It gives us a common on that. And we get two voltages out of it very, very easy. We get a low voltage and a high voltage. Then delta, it's hard to get two voltages out of it, but we get more current in the primary, work out of the primary than we do in the individual lines feeding up. So each one of them's got their own. So we can get power. We can it takes the voltage is constant, so it varies with so the current varies directly with voltage, right? You understand that? So most power is transmitted using delta. And then when you get it into a business, it's usually Y, because Y gives us that Y. It gives us that common connection that some people call it star, by the way. So we have a transformer that basically we can wire our primary different ways. We can either wire it to get a divide by 2 or divide by 4. So we can either hook the primary in series, or we can hook the primary in parallel. So which one would be high voltage and which one would be low voltage on the input?
Low voltage would be I'm sorry, in parallel.
In parallel, because it requires more current. The primary requires more current, right? So high voltage, we would hook the primaries in series. The low voltage on the input, we would hook the primary in parallel. So H1, H2, I forgot to turn it on. So we always bring our voltage in on H1 and H2, and then we jump it, right? You understand? Okay. So this would be, so if I counted the number of turns, I put twice as many turns in the primary than I have in the secondary, so it would divide down, right? Over here, we're having the number of turns in the primary, but we're sharing the current. So if this was 2 amps and this was 2 amps, then if this primary was 2 amps and this was 2 amps, then my input could be 4 amps because they're in parallel, right? Okay. Over here, if this is 2 amps, this is going to be 2 amps, and the line's going to be 2 amps because they're in series. But over here we have a higher voltage, right? You understand that? So what determines the power in the circuit? What determines the power delivered in the circuit? The load. The number of windings don't determine the power. The number of windings determines the voltage. The load determines the power. So if I turn on these light bulbs, it has nothing to do. I just got to give that load. The load is rated to deliver that power at a certain voltage. Right? You understand? And then the transformers provide the voltage and they provide the current to get the power. Right? You understand that? So over here, this is going to be the same. So this should be 120. And over here, this is still less, guys. And this should be 120. And over here, this would be 240. And over here, this would be 440. We still get 120, but what determines the power in the circuit is the load. So technically, if I turn on a 100-watt light bulb at my house, how much power is Alabama Power going to give it? 100 watts. But we know they got to give them more because the transformers are not 100% efficient. So the load determines the power, right? But the load is going to be rated at a voltage. You can't take a device that's designed to run on 240 and hook it up to 120. You'll get a quarter of the power. And you can't take a load that's designed to run 120 and try to run it on the 240. You'll try to get 4 times the power, right? And it'll burn it up. So loads are designed around a certain voltage to pull that current that's designed to deliver that power. So no, the coils have nothing to do with power. Power, what determines power? Now the transformer's got to be rated at a current that can provide that load, right? You understand? So currents are rated they're not rated in watts. Currents are rated in usually kVA, especially industrial transformers. Kilovolt amperes, because this has got to deliver what we call apparent power. Well, AC and DC are not the same. AC, and I'll try to show y'all that if I got a capacitor up here. I do have one. AC actually creates phase shifts in a circuit. So we end up with power that appears to be there, but it's not. And so transformers are not rated in watts, they're rated in apparent power, because they have to deliver apparent power. We talked a little bit about that, right? AC causes phase shifts. I had a coil of wire, and I would start winding it up, and you'd watch the current and the voltage. The more wires I put in there, you'd cause the current and the voltage start shifting away from each other. So what we're going to do, of course, the transformers are actually these dual secondary transformers. The primary is actually set up like this. So this is the way it's drawn in the textbook. Some of the textbooks are they draw it not right, so it's a good idea to look at the label on the transformer itself, because they'll usually show you how to wire it if somebody don't tear it apart. The primary is actually wired like this. So this will be H1, this will be H2, this will be H3, and then this right here will be H4. Why do they do that? Huh? Huh? You don't have to cross wires. So when you buy these transformers, they'll come with those metal jumpers, right? You understand? And you don't, so if they wired them the other way, I would have to cross wires. So it prevents us from having to cross wires when we wire. So it's real easy to find out. Don't understand that? So if I wanted to wire them let me change colors. If I wanted to wire for low voltage, I would just jump this and just this. And no wires do what? No wires cross, right? You understand? If I wanted to wire it for high voltage, I would come over here and do this. And still no wires cross. So now we can use these metal tabs that come with the transformer and just stick them in there to do that. So it looks weird, but that's the way we do it. So this would be in what? This would be in series. So this would be for high voltage. And then for parallel. Now, what we're going to do when we do this layout, is we're going to wire the transformer. We'll start off wiring it for low voltage. And then it says, then we're going to wire it for high voltage. Well, we're not changing our 208 in, right? You understand that? So what's going to happen is we're going to actually see the division ratio when we divide. It's not going to hurt anything. But we're not going to skip over the part where they say wire it for high voltage or wire it for low voltage. We're going to wire it for both of them so we can actually see it. Are we okay? Any questions on that? Okay. So does that y'all's book have it drawn right? So some lab books, they came them out and they actually had the diagrams wrong. They were drawn the same way. So yours does have it crossed like this, right? Okay, so you okay? The next slide, of course, now these are the chapter quizzes. And where are these at now? These are online, right? Okay. Inside where? Inside the lab section. So logic. So these are logic. So this is where we're going to come in and actually wire our circuit. Oops. Oh, So the first one, what logic is this? Anybody know? Yeah, this is and, good. And so we're gonna wire this up, we'll use push buttons. I think we got one of our push button station has two normally open contacts. Now you have to understand on the and we can do what? We can do 15 or 20 of these things. We're just going to do this. All we're trying to do is see the logic, and we don't have enough push buttons to get more than that. They're only showing two. Right? Everybody okay? Now what we're going to do is, and you need to put your push buttons close together. Like that, like I said, we shouldn't have any problems with this one. We got one that's got two normally open push buttons. It's got a, there's two green ones, it's got a black. And it's got a black one. Or it's got a big one. That was the one. The diagram on top of it, right? So you can do that with one push button. You can do this side with one push button. So everybody okay on this? Anybody got any questions on this? So what are they doing? Well, what they're going to do is you're going to check for short circuits. Okay. I can't. Let's see. Let me do a. I can't draw. Oh, I can too. I can't remember. I can't remember what to do. Now I can. This screen capture software lets us draw, but I can't remember how to do it. So what we're doing here is we have our ohm meter. Everybody got their meter, right? Okay. And it does ohms, right? So what we're going to do is we're going to check for a short circuit. One thing you're going to find out is the resistance of a transformer is extremely low, especially this low voltage side. Cause it's got more current, right? And the only thing that, transformers have what we call X of L built into it. And that's one of the reasons they don't burn up when we put AC on them. But you never want to put DC on the transformer. Cause then the only thing that's limiting the current is the DC resistance of the conductor. But what we want to do is we want to check for short circuits. And the best thing to do to check for short circuits is to use your ohm meter. So we're going to disconnect one of the wires. And why we're going to disconnect one of the wires? Because if you put it between L1 and L2 with power off, we want to make sure power's off. Of course, I'm controlling that. You don't ever want to put it on there to equalize for our own meter or the power's going to be off. We're going to pull one wire, so now we're not reading the resistance of the transformer. Does that make sense? Okay. And one of the wires, the ones they're recommending what we call L2. Now the transformer, they're not labeled X1 and X2. They're labeled X2 and XL. What do you think of XL means? Well, when I look at a transformer, what do I see right down below the transformer? I see something that starts with an L. What does it start with? What is that? It's a P. So they change it. So the X1 side is the P, right? So that's what they're labeled. We go right here, it's called X and XL. That's what they're labeled. XL is the P side, X2 is the unseen side. Now we're going to start our test at L1 and L2. Which one's gonna be L1 and which one's gonna be L2? Fuse side, which one's gonna be the fuse side? L1, you're exactly right. Remember that when you wire it, right? So that means this side right here, this is gonna be the fuse side. So what we're gonna do is pull off the what? We're gonna pull off the unfused side. We're gonna put our meter right there on that banana plug and we're gonna measure right here. We're gonna push both those buttons in. And I'm gonna measure probably around maybe 1,000 ohms because we should measure the resistance of the light bulb. And those are incandescent bulbs, guys. These are all incandescent bulbs that we're using here. You know. If you measure real low, what does that mean? It means either you're reading across your transformer. You don't want to read X2. You don't want to read the wire that you pulled out of X2, right? Between the wire you pulled out of X2 and then XL. Are we okay? Yes or no? Questions? We're gonna measure the resistance of the light bulb, and I don't remember what it is, but it should be real close to zero. You're gonna put the manufacturer numbers up here. So you're gonna put the manufacturer numbers on each side of which switches you decide to use. You put the manufacturer numbers of the light. We've got one. We got two light bulbs. We got a red one and a green one. Which one you use is up to you. They don't find it. So we should only have two stations up here for this one. One of them, the one that's got two push buttons on it, and one light bulb. Are we okay? Any questions? Yes, no. Yes.
Well, we want to start the circuit first, and then.
Oh, here's the light. Here's the one that's got the light on. So this says two normally open. This is your light. So these will be the only two modules and stuff. And then you got one normally closed. So this is manufacturing on. Yeah, I got to put you next to that. So here's the manufacturer numbers for these two. This is actually drawn as a normally closed. We're not going to use this guy for this lab. We're going to use these two right here. These are the manufacturer numbers. So one of them is 1 and 2, and the other one is 3 and 4. I think I can't read. That's it. 1 and 2, no, 5 and 6. Oh, I'm sorry. This is a double pole single throw. So you got to wire it for the normally open. So you'll be using 4 and 7. So you can use these for the knots and nands too. So it looks like this push button station right here will do all these logic labs. Because all we're gonna have is two push buttons. So y'all understand that though? These are double pole, single throw, right? Very okay. So we get a normally closed and we get a normally open. Okay. And of course our light. Very simple. We're not going to use the selector switch yet. So here's our lights. These are the manufacturer numbers that we'll wire them to down here, right? So before you wire the circuit, what's the first thing you're going to do? Before you wire the circuit, you're going to write those manufacturer numbers. Okay? And then that way you're wiring numbers. You got to know the different components. Oops. I wanted to leave that up. So what logic is this? Oops, sorry. Or, yeah, same two buttons, right? You're just gonna rewire your circuit. So your components are not gonna change. You're gonna leave what? The push button station up there, the dual push button station, and then the light, the one with the light. Any questions on this circuit? Everybody okay? Right? Everybody okay? Yeah, we're gonna do that. We'll do it on every circuit after we wire them up. Then we'll come in and wire this circuit up. This is a what? No, it's only got one push button, right? Same push button station. Those double pole, single, double pole. I'm sorry. Single pole. Well, it's double pole. It's weird. It's got two poles, but it's got a normally open and a normally contact available. But technically, it's not a double pole, double throw because it's got two poles, but one of them goes to a normally open and one of them goes to a normally closed. Does that make sense? I didn't say that right a while ago. So this is a knot. Then what we're going to wire up next. What logic is this? It's not a name. I don't say all about that. So does the light start off on or does the light start off? Yeah, so if it starts off on, then that's your knots, your nans, and your no's. And I'm looking for the terms any or all. If I say any, it's either or nor. If I say all, it's either an and or a nan. So what would I say about this? Push button, turn the light off. So if I push this button right there, that wouldn't break the circuit. If I push that button right there, that wouldn't break the circuit. So what is this? Is this a nan or a nor? Nor, right. Now over here, the light starts off on, which is, I know if it starts off on, it's either what? A nod, a nan, or a nor. What's required to turn the light off here? If I push this one, would that turn it off? No. If I push this one, would that turn it off? So I have to do all of them. If I have to do all of them, then this is a nan, right? Understand? So this is our logic. So, and of course, you got to draw some circuits there. We're not going to do the lab on the logic relay. Their logic relay is just a relay that they wired to do logic. So it's a waste of time. So they don't have, so I don't know why they did that. So their relay is just a relay that's wired. They jumped the relay to do logic, which is what they're doing anyway. So we're okay there. So we'll skip over the logic relay. Do the chapter quiz. What comes next? Is basic control circuit, is BC next or LD next? BC. We're not going to do troubleshooting in the test light. I think I've got the layout on that, which we're going to do. So what's the difference between troubleshooting with a test light and troubleshooting with a meter?
Maybe more accurate.
Well, a lot more accurate. A test light is either going to come on or go off, right? But it's a very simple tool that you can use. You still clamp one side of your test light on one side, and normally it's a neon bulb. Neon bulbs require like 70, 80 volts to turn them off. So odds are if that neon bulb comes on, then odds are the voltage is okay, right? You understand? But you're right. So meter's a lot more accurate. We actually know what to. Test lights give us a what? About what they. So we're not going to do the test light. This is still test light. Test light. And this is the circuit that we're going to do. What's wrong with this circuit? Yeah, it looks like we have multiple loads it looks like we have multiple loads in the same line. That's illegal, right? You understand? But this is a troubleshooting line. So what we're going to do is we're literally going to put, and this is probably one of the hardest ones for y'all to wire, guys. So what we're going to do is these are two normally closed push buttons. So what happens is the first time and this is a memory circuit, right? You understand that? Huh? I'm listening.
What page is that?
I don't know. It's in the DC section. Yeah. 25. Is that right? On y'all's love, this book right here might not be. So this is a memory circuit. Are we okay on that? Y'all understand that? Yes or no? So we start off with these two normally closed push buttons. So we can use that same push button station that's got the ones that we can either wire as normally open or normally closed. So these start off normally closed. I press the start button. It brings in this control relay. Control relay seals itself in. Everything's okay. I'm going to measure the voltage across the control relay. We should have 4 volts across the control relay. Everybody okay? Then what happens if I push one of these buttons right here? Now let's say I push this one. We're going to put this load right here in series. So now this guy's going to drop some voltage, and the voltage to our control relay is going to drop down. Is the light going to come on? Why? No, it's not. Why? Because power varies with the square of the voltage. That bulb's rated at 120 volts, and we're giving it maybe 30 volts. So it's on, but it'd have to be pitch dark in here, and we'd have to turn out all the lights, and you'd probably barely see it. But power varies with the square of the voltage. If it goes down, it's 1 over the square, right? You understand? So CR, well, it might drop out and it might stay in. And then what we're going to do is we're going to press the second one. Now, when we press the second one, that's going to put 2 in series, right? You understand? And now the voltage across CR is going to drop down way low. And hopefully it will drop out. But to measure the voltage, you're going to have to get help. I might have to come over and help you. If to measure the voltage, we're going to have to push all these in at the same time for you to measure the voltage across the cord. And what we're trying to see is what basically, so relays have what we call a pull-in voltage. So they generate enough current to generate the magnetic field. And then it has what we call a holding current or a holding voltage. So that's how much it takes to keep the magnet pulled in once it's connected. Which one would be the highest? Yeah, the pull-in's highest because the armature is not even touching, right? You understand? So it's got to create a strong enough magnetic field to cause this armature or this plunger to come up there and clamp in. Now, once it's clamped in, it don't take near the magnetic field to hold it, right? You understand that it did to what? To pull it in. So, and that's what we're gonna look at. We'll see if we got both of them in, odds are we can press the start button all day long and it won't energize. But once it's energized and I press both those buttons, sometimes it drops out and sometimes it don't. Because it all depends on the relay, right? You understand that? So this is going to be troubleshooting. We're going to get used to using our meter. This is where it's going to be touchy. This is where we might have to get help. We might have to defeat the social justice. In fact, what I might do, guys, I might wire this up myself, and we'll do this as a class. Because this guy right here, people make mistakes on that all the time. But if you do the manufacturer numbers, you shouldn't have that much problem, right? You know what I'm saying? So y'all can skip over this one right now. We'll do it as a class, okay? Then we have the next one is BC3. So I think BC3 is on the list, right? Anybody got their lab sheet out to see which ones are the BCs we're going to do? Okay, so this is 2. So 2 we're going to do as a class. No, I'm sorry. Fuck it. We're not doing 3? Okay, so let's look at 4. So 4 we're going to be introduced to a limit switch. This is a solid state limit switch. And everybody got one of those, right? What's a limit switch, by the way?
Once certain company reaches a certain thing, to switch it.
Yeah, well, we have mechanical so this is an electromechanical one right here. So it's literally got a mechanical operator that when something hits the limit, it'll come up here and do what? Change switches. So this guy here has got a normally open and a normally closed. That's available to us. So it depends on which one this is inside this plate right here. We got one that's opened up. And you can literally hear it clicks when it's made. Can you hear it? Well, what's a solid state limit? So this would be the symbol for a limit switch. So a limit switch basically has this little ramp symbol right here, but it's inside a triangle. It's not a triangle. It's inside a square, a diamond shape. Okay. Now this guy here is a solid state limit switch, so it's electronic. It's on the PowerPoint. This should be open by the way. So it's got this guy right here, right? And then what else do we have? We just got some type of load, a light to start off with. And it's drawn inside a diamond, so it tells you right there it's solid state. Now, we're dealing with 120 volts. and we'll talk about this later. So that means this guy, the electronics is going to power through the load, right? You understand? So what's going to happen is this guy here is going to drop right around 4 volts. It's not a switch, it's electronics. Electronics will always drop a little bit of voltage, and it's got to power itself, right? But still, that still leaves us 116 volts over here to work with. Plenty to run the light bulb, right? That makes sense? Okay? So we'll measure across this thing. I don't know if we do it in this class or not. You definitely do it if you take a sensors class. So that way we have a voltage drop. If we got a voltage drop, that means we have power available to run the electronics. This is called a 2-wire sensor. And, this right here would be bright. No, this right here should be, gosh dog it, I should know those colors there. This would be brown. I'll have to look at it. We have what we call 3-wire sensors. These are usually operate off low voltage, like 24 volts or stuff like that, because now if we operate off 24 volts, we can't afford to have a voltage drop across the sensor itself. Does that make sense? I know it's so a 3-wire sensor, they'll add another wire right here. So this will be connected to L1, this will be connected to L2, and then this right here will be connected to this right here will be connected to the load. So now the sensor is actually what? It's actually powered. So the sensor that we'll use is a 2-wire sensor. So it's only got 2 wires, and it's AC. So it doesn't really make any difference which way you hook it up, but it does because you want to maintain the code between your 2-wire sensors and your 3-wire sensors. So this over here is going to be blue, I hope it is. And then this right here will be this right here would be brown. So you need to make sure the blue goes toward L1 and the brown goes toward L2. That way a 3-wire sensor is a little different. So a 3-wire sensor, the load there. This will be blue. This will be brown because it goes to L2, right? And then the signal wire will be black. The 2-wire sensor, the brown goes toward L2, always goes toward L2 unless you got that. And then we have a 4-wire sensor. This right here is normally open. And then we have a 4-wire sensor. If we have a 4-wire sensor, this right here will be white. And this is a normally closed. On solid state sensors, that's it, guys. We got one contact, or we might have a double. It might simulate a single pole double throw, where you get a normally closed and a normally open. And the white will be normally closed, and the brown will be normally open. And I can show y'all some of these. We have one. So ours is a 2-wire sensor, so it's designed to work off a higher voltage, so we can afford to drop a voltage to generate the power that it needs to run the load. That means to run the electronics inside. But you get to most of these sensors now are operating on 20. And what's the problem with 120 volts? So why is most control circuits like 26 volts AC or around 24 volts DC? That's exactly right. Because NAC 70E has specified anything above 50 volts is considered to be a lethal voltage. And that means we're going to have to start wearing what? additional PPE, right? So, but you're still gonna run into, in older installations, you're really gonna, 120 volts was the control voltage for years, 10 years. So you'll still, in older installations or installations that's been around for a while, you'll probably see a lot of 120 volts on their old stuff, and then 26 volts AC or 24 volts DC on their new stuff in their control circuit. So okay, let's see if there's so solid state limit switch. We're gonna do that one. What's the other BC we're doing? So here's 6. Let me get 5. Here's 5. So we're still going to use the solid state limit switch on 5, but we're going to add a control relay. Are we okay? Are we okay on that? Let's see where I'm at. I'm on BC 42 on my book. Any problems on that? Are you okay on that circuit? Yes, no? I'm waiting. Because now's the time to ask questions, not when we get up there wiring circuits, right? Y'all understand that? Oops, I didn't bring my camera up. Let me see if I can. So here's 5. So we're going to use a control relay and then 2 lights. So here you'll have to use the red and the green one there. And then we'll use the, by the way, ours is our control relay is a 3-pole double throw. So I don't know the numbers on it, but notice on that wiring diagram down here, they got a normally open up here, and then they got a normally closed up there. And both these go to different lights. And they're coming off our control relay. Well, if you look at our control relay, it's drawn like this. And I don't remember what they are. Let's just make up something 9, 10, and 11. So this is already done for me, right? You understand? So all I gotta do is, this is 9, and then this over here would be 10 and 11. You don't have to run that wire because it's what? It's inside the relay. So I've seen people, they'll come up here and use 9 and 10, and then they'll come up here and use another pole, so they can get their normally close. And it may be 5, 6, and 7. So they'll do 5, 6 for one of them, and they'll do 9 and 11 for another one when they just could have done what? They just could have wired it like that. So, and there's 3 poles inside our control relay. There's 3 poles, double throw inside our control relay. And then what's 6? Okay, 6 is our first memory circuit. Is this the right circuit? Oops. Oops, maybe not. So that's going to ask you to draw where you would connect the meter to make different measurements. Can y'all see where whoever did this put the manufacturer numbers on there? You'll see those? And where's that information? So once you got the numbers, this is not a solid state relay. This is not a solid state sensor. This is a limit switch. So that's where you have to use the mechanical limit switch, right? You understand that? Here's a start, here's a fill in, this is our selector switch. Ours is a 3-position selector switch, but it's got, I don't know what, I don't, yeah, I do have it. Ours is labeled manual and auto. They're calling theirs memory and no memory. Okay. So what are you going to do? You can use manual and off, or you can use auto and off, whichever one you want to use on this right here. Everybody okay? Yes or no?
So, okay, cycle timer to that. Like a cycle timer on that.
Where we at? I'm on B46. This is lab 6. Huh? Yeah, like I said. This is lab 6, right? Huh? Not well in my book. Okay. So this is a,
Cycle timer, that internal too?
where's cycle timer at? Oh, no. This is not a limit. Let me find our cycle timer. See, I've only got one part from somebody's station. I need that. Yeah, there's supposed to be a cam on this thing right here that you can adjust that when the motor turns. So it's got a little motor in here, a little small synchronous motor in here. And when you turn it on, it starts rotating. Well, we're not even going to do that. It don't show the motor circuit on here. So what we were going to have to do is we're going to have to take the cam and rotate it to either make the what? Make the little limit switch make or break. So on this one, you can just use it this way. Or you can use your limit switch. What's that a symbol for? So instead of using the cycle timer, let's use the limit switch. Well, what type of limit switch is this one? We got several symbols we learned. Huh? Yeah, it's normally closed. So what's the 4 symbols? We got normally closed, normally open, normally closed, held open, and normally open, held closed. Are you okay on those symbols? Anybody need to see them or understand them? So this is a normally closed limit switch. So instead of trying to use that cycle timer, because it's so hard to do anyway, because what you'd have to do is you'd have to grab that cam and manually turn the thing, because we're not going to hook up the motor. Just use your limit switcher. And this one's missing anyway. I don't even know why we need a cycle timer, because this is the only lab right now that it's in this character. So I didn't see cycle timer. Thank you. I'll just mark that out. And then we'll use it only closed. So basically it's going to act like a stop. We press this button, touch that button, it's going to bring in CR. It's going to sit, the light's going to come on, it's going to seal itself in until you do what? Until you hit the limit switch. When you put the selector switch into the no memory, normally what we would call this is we'd call it run and jog. So what do we do when we jog a motor? We just run it in burst, right? Usually the position. So this is a standard jogging circuit if it was hooked up to a motor, but it's not. It's a control relay. So if I put it in memory, then when I touch that button right there, it's going to energize CR. This is a CR contact. It's got the same name, and it's going to seal itself in. So now you can let go with the start button, right? Everybody okay there? Okay. Until I come up here and activate the limit switch, and it should drop out. If I put this into the no memory or the jog position, this is going to open this contact right there, and what I've done is I've taken away the sealing circuit. So now when I press the start button, the CR will come in, but this contact's going to close, but there's no circuit, right? You understand? When I let it go, it's going to cut off, so every time we press it, CR is going to come in. Every time we let it go, CR is going to drop out. But don't use that cycle timer, because like I said, you'd have to turn that cam to do what? So just mark out cycle timer and put it in the system. So that's all the BCs. So we should have enough lab. So if y'all got any questions on these labs that we've gone over, we did logic, right? And we looked at ands, ors, nands, nors, not. We looked at the troubleshooting lab, but I'm going to wire that up on one of these trainers that's not being used if I can find parts. I'm sure we've got enough around here. I'll probably wire it up on this trainer right here. Then transformer, you're gonna wire your transformer for low voltage. Then you're gonna wire it for high voltage. You make the measurements and record those in your lab book, right? Are you okay? So we did the power supply, the second power supply lab. I think most of y'all finished the first power supply lab. We did we went over how to wire the transformer, right? Everybody okay on that? Of course, y'all gonna jump y'all. Y'all don't have the little metal tabs like that's on the blue trainers. Y'all gonna actually jump those with the small wires. By the way, you can see how all the trainers are set up. All the jumper plugs all the jumper wires are on the left hand side, right? You understand that? We don't want to see any modules up there. We want to try to keep it clean as we possibly can, so we don't get confused when you're in there dealing with a lethal voltage. Everybody okay? Are we ready to go lab? Test review is up there, I think. I shipped the test. I thought the test was Thursday. Well, when I looked at my calendar, I realized it was supposed to be tonight. So I hadn't put the review up there, so y'all got a reprieve on that. Let me make sure the test review is up there. I'm going to stop recording.